Good morning. So I'm especially honored and excited to introduce Dr. Michael Kearns for our morning keynote because in addition to all of the extraordinary success that he's had, which I'll tell you about in a moment, little known fact is that a little over 3 years ago, Michael introduced me to a small startup named Quantopian. So actually at this conference. So Michael Kearns is a professor at the University of Pennsylvania for their Computer and Information Science Department. He's also a founding director of Penn's Warren Center for Network and Data Sciences. His research interests include topics in machine learning, artificial intelligence, algorithmic game theory, computational social science, and quantitative trading. He has consulted and worked widely within the technology and finance industries and is chief scientist at Mana Partners, a quantitative hedge fund and trading technology firm here in New York City. And Michael is also a scientific advisor to Quantopian.
Okay, good morning. Thanks to all of you for showing up so early on a Saturday. Anyway, thanks for coming and thanks very much to the Quantopian team for having me. So I noticed in the program there are a lot of talks that are on the discussion of overfitting and train test methodology, et cetera, which is all good stuff. But one way of avoiding overfitting is to never assume in the first place that the future will have anything at all to do with the past. And that's what I want to talk about today. As you can see, many talented people have given deep thought to the concept of regret in the past. But I'm here to talk about a particular technical definition of regret and to tell you about the subfield of machine learning, which is called no-regret learning, which is a thriving subfield of machine learning and is finding wide applications in many domains. And today I just want to tell you about what the basic framework is, the kind of result that this field produces theoretically, and then talk mainly about potential applications of it to trading domains. And you know, if you're fundamentally suspicious of a title like Trading Without Regret, your instincts are correct. And you'll notice that I've added an asterisk to my title, which we will come to eventually. Okay, so what is no-regret learning? I just want to, on one slide, kind of describe the technical framework for you. So no-regret learning, in the basic no-regret learning framework, I want you to imagine you have some set of n signals or predictors, and I want you to think about these signals or predictors in an extremely general way. So to give examples of what these signals or predictors might be, they might be the time series of returns of individual equities or other instruments or funds of these things or portfolios of such instruments. Or they might be full-fledged strategies like black box algorithms that are taking any data sources you want as input and producing, if you like, predictions about the future. So you might think of them as alphas, for instance, in a trading context. Or they might be, other sources of data or information like advisors, like stock analysts who are giving upgrade and downgrade recommendations, or sentiment indicators from news or social media, anything you want. You can really think of these things as just boxes that have unknown inputs and are generating a sequence of numerical values. And each trading period, we're going to imagine that each one of these signals receives some arbitrary payoff. And when I say arbitrary, I mean I'm going to make absolutely no stochastic assumptions or probabilistic modeling whatsoever. In particular, you can think of the returns or payoffs or losses of these black boxes as being generated by some omniscient or even omniscient nature or even adversary whose express purpose is to sort of foil your use of these signals. And so you should already be wondering what in the world could you possibly hope to say in such a setting, and I'll come to that in a second. And in particular, these signals or black boxes might have all kinds of side information or even inside information. They might have expertise and specialization that lets them do well under certain conditions and poorly under other ones. And so the only thing I'm going to assume about kind of the vector of payoffs that these n predictors get at each time step is that they're bounded, okay? That they're not arbitrarily large, either positive or negative. And note that this assumption is already present in most stochastic models that are used in finance, such as the transition from discrete Brownian motion to continuous Brownian motion that underlies things like options pricing, okay? So in this setting, your goal is to design an algorithm that's going to maintain some portfolio or dynamic weighting, or if you like, a probability distribution over these n signals or predictors. And whatever probability distribution or weighting you're using at each time step, you're basically going to get the weighted average, according to that distribution, of the underlying payoffs for the signals. Okay? And so what's the goal? So I've set up this extremely general setting where you have these arbitrary n black boxes. Your algorithm is maintaining some weighting or distribution over them, but there's no assumptions at all on the sequence of payoffs. And so in particular, there's no assumption here that future payoffs have anything to do with past payoffs for these n signals. Well, so in the absence of there being some relationship between past data and future data, the only thing you might hope to say is something about the past, about your performance in hindsight on the data so far. So no regret learning, the goal is that no matter what the sequence of payoffs is for these underlying n signals, your algorithm should have what's called no regret, which means that if we look at the payoff of the best one of these signals in hindsight, that your algorithm's payoff is not too much worse than that, okay? So, that's what I'm sort of saying informally here. No regret is going to mean that if we look at the best payoff, meaning the best payoff amongst these n signals in hindsight, and we look at the actual payoff that your algorithm got in hindsight, that the difference between those things is sublinear, right? So if t is the number of time periods so far, we'd like, for instance, results like this difference of the best payoff minus your algorithm's payoff growing, say, like square root of t. Because if it grows like square root of t, then if we look at your per step regret, right, that's square root of t divided by t, which is 1 over square root of t, and that's going to 0 as the number of periods increases. And this is the source of the term no regret. So no regret refers to having per step regret that diminishes with time, which is equivalent to having sublinear cumulative regret, okay? Now, So this is the goal, and so it's a form of learning, but it's a form of learning in which you're not generalizing in any sense at all. You're just claiming that at all points in time, you're sort of tracking the best one of these n strategies or predictors in hindsight. Okay, so it's an ex post statement rather than an ex ante statement. Now, let me point out something that we're not proposing here, which would be deeply suspicious. We're not competing with the optimal unconstrained policy that can switch willy-nilly between the different strategies or predictors, okay? So we're not sort of saying, like, in hindsight, we should have been doing this on, following predictor 1 on the first day, predictor 7 on the second day, predictor 19 on the third day with arbitrary switching. We're just comparing ourselves to predictor 1 in isolation, 2 in isolation, 3 in isolation, and whichever of those is best, we want to track that, okay? So this is the basic definition. Even though there are a lot of deep mathematical connections between boosting, which many of you may be familiar with, and no regret learning, the fundamental assumptions of those two frameworks and the goals of them are quite different. So in boosting, you do make probabilistic assumptions. You make stochastic or distributional assumptions on how the data is generated. You essentially have an IID setting. And there your goal is to actually beat the best of your weak learners, so to speak. Here, we're not trying to beat the best, right? We're just trying to track the best. And so you can think of the criteria here as being the difference between finding a needle in a haystack, i.e. the good Quantopian strategy out of the sea of Quantopian strategies versus the other challenge of trying to build something that's better than any one of the individual strategies in the first place. Okay? Now, no regret learning, this framework has obvious appeal in financial settings where, in particular, non-stationarity is the rule, and in fact, even worse than non-stationarity, a lot of that non-stationarity might be generated by game theoretic or strategic or even adversarial interactions between multiple parties. And so typical time series models even aren't appropriate. Okay? Okay, so this is probably the only semi-technical slide, and I'm only going to talk about the highlighted parts for the most part. So in the top box here, I've reproduced from a survey paper on no regret learning that I'll give a reference to at the end, what a typical algorithm that achieves this no regret criterion looks like. And the first thing I want you to notice is how simple and how short it is, right? If you coded this up in MATLAB in full detail, it would be maybe 5 or 10 lines inside of a loop. And these algorithms are sort of very appealingly simple, and almost every no regret algorithm looks more or less like this. you would essentially have a weight associated with each one of the n signals, and you're going to adjust those weights in a semi-obvious way according to historical performance. And in particular, the way you're going to update a weight at the next time step is you're going to say the new value for the weight is the old value to the weight times some multiplicative factor. This happens to be phrased as losses rather than payoffs, so negative values for this signal m are good and positive is bad. But in plain English, what this update is basically doing is saying, look, whatever your payoff was, I'm going to increase your weight by a multiplicative factor of 1 plus something times your payoff. And if you lost money, I'm going to multiply your weight by something less than 1, which is going to be 1 minus something times your payoff. And the something here is this single free parameter of this algorithm, which is a learning rate, okay? So I have one knob, and if I kind of crank that knob up very high, then I'm making very, very radical changes in response to positive or negative payoffs. I'm going to greatly upweight things that get slightly positive payoff and greatly downweight things that get slightly negative payoff. If I set that learning rate very, very low, then I'm making much more modest changes. The important kind of algebraic part of this update is that it's multiplicative, it's not additive. So those of you who are familiar with things like the perceptron learning algorithm for linear threshold functions, which has nice mathematical properties, that's an additive update. You sort of say like, well, I'm going to add something to the weight if it got a positive payoff, and I'm going to subtract something from the weight. Here we're actually multiplying things. And so in particular, if one of these signals goes on a run of positive payoffs, it will exponentially increase the weight of that signal over that period of time, okay? And then the way you're actually making your decisions at each round is just by playing the weighted average of the underlying signals according to the normalized distribution given by these weights, okay? So that's the algorithm. It's incredibly simple. And here's a very, very nice theorem you can prove about this algorithm. And I'll just go through sort of the final part. This theorem is saying, look, if you set the learning rate of the algorithm in a particular way, then what this pink box is saying is that the payoff of this algorithm on an arbitrary sequence of payoff vectors for the underlying signals, the payoff of this algorithm at the top will be the payoff of the best one of the underlying signals in hindsight minus something that looks like square root of t log of the number of underlying signals. Okay, so let me say that again because and I want you to keep just this one algebraic expression in mind. The payoff of this algorithm will be, no matter what the sequence of underlying payoffs for the signals is, the payoff of the algorithm will be, at worst, the best payoff in hindsight of any of the signals minus the square root of t, which is the number of time steps, times log of the number of underlying signals that you're tracking, okay? So there is a penalty here for how many signals you're tracking, as there should be, and I'll say something a little bit more precise about that in a second. There is a penalty for that, but it's modest, it's logarithmic, okay? Okay, so let me just make some miscellaneous remarks about this framework and type of result. So first of all, no-regret algorithms and the analysis of them have actually a very long and rich history. It goes back at least to kind of the game theory, micro-econ literature in the 50s in the form of something called Blackwell approachability. It has a very large and very currently active, as I mentioned, machine learning literature. There are lots of connections to finance, some of which I'll talk about, but a couple of others that I won't. There are modern connections to Black-Scholes. So in particular, it is possible to derive the Black-Scholes pricing formula without any probabilistic assumptions whatsoever by essentially viewing the pricing process as a game between a price setter and an arbitrageur, both of whom are playing a no-regret algorithm. This was done in the last few years or so. There are also very close predictions between no-regret learning and the right way of pricing in prediction markets in order to elicit truthful information from an underlying population. There are very strong and long-standing connections to game theory. You can derive the minimax theorem, and you can also derive linear programming, again, as the limiting behavior between two parties playing no-regret algorithms in a zero-sum game. And more generally, if you take two no-regret algorithms and have them play repeatedly against each other, so they're each generating the payoffs for the other one, in an arbitrary game, zero sum or otherwise, you get convergence to Nash or a more general notion of equilibrium called correlated equilibrium. Now, this all sounds great and very powerful. Let me make a couple of remarks, though, that will demystify this kind of result and this framework. So first of all, you know, a lot of what's difficult about proving the type of theorem that I gave on the previous slide is to really deal with the case, to really deal with arbitrary sequences of payoffs for the underlying signals. So in particular, you know, here's an algorithm that won't meet the no regret criterion, but you can still say something about. So it's just the greedy algorithm, which is known in the no regret literature as follow the leader, which is all you do is you basically say, well, I'm going to look at the payoffs so far, and whichever one of these underlying signals has the highest cumulative payoff so far, I'm going to put all of my money or all of my weight on that particular signal tomorrow, okay? And then, you know, then tomorrow happens and you update everybody's data and you repeat, okay? So this is sort of the most naive algorithm you can imagine. It does not meet anything like the result I gave on the previous slide, but on the other hand, what you can say is that the regret of this algorithm will essentially scale like the number of times that the lead changes in the underlying signals for the n predictors, right? Because the only time you sort of lose is when, you know, you went with expert 5 or predictor 5 and, you know, they weren't the best and then they actually lost the lead. So, you know, if you happen to have a collection of underlying signals in which the one that's the best doesn't change that often, then this algorithm will work perfectly well, but in general it'll do poorly, okay? Maybe a slightly more related but more mathematical thing to say is that even though this log n term in the regret is modest, it means that you can't try anything. Okay, so here's something that, you know, doesn't work and shouldn't work, which is imagine that what's going on is that nature is flipping a sequence of fair coins, and these predictors that you have are trying to predict what the outcome of the coin is going to be each day. Okay. So you're going to try to look at the predictors and use their guesses as to what the next value of the coin is going to be to make your prediction. Okay, so I think we can all agree that the result I gave on the last slide better not say that you can predict the outcome of a fair coin better than random guessing. And in fact, it doesn't, right? Because in order for there to be an expert or a predictor in your pool that's good, you'd essentially need to add as predictors all 2 to the t possible sequences for this sequence of coin flips, right? And you'll notice that if you choose n equals 2 to the t, then log of 2 to the t is t, and then when you take square root of t times log t, it's square root of t squared, it gives you exactly square root of t. Okay, and this is as it should be, right? What it's saying is that you can use this method to kind of come within predicting the outcome of a fair coin, making sort of like 1 over square root of t, you know, which is exactly the variance, right? The standard deviation. Okay, so it's not telling you that, you know, impossible things are possible, which is good. On the other hand, it's often the case in the no-regret literature that you find that when you do make probabilistic assumptions of some kind on how the data is generated, and you run a no-regret algorithm which is not using such assumptions, that no-regret learning algorithms often, in fact, give you optimal or near-optimal solutions for your particular stochastic assumptions. So this is a very nice thing because it means that you can have these worst-case adversarial guarantees no matter what the data is, but if the world is nice to you, you might actually enjoy the optimal result for that nice set of assumptions. Okay, so now let's turn to trading. That's background about no-regret learning. So the use of no-regret learning in trading or finance settings is not new at all, and what I've reproduced here is the cover page of a very famous paper on this topic called Universal Portfolios by Tom Cover, who died a few years ago but was for many years a prominent statistician at Stanford. And in his paper, his paper actually predates the kind of modern flurry of research in the machine learning community on no-regret learning. And he was considering a setting in which these n predictors were just simply the returns of stocks. Okay, so you have you see historical returns of stocks. He's not going to make any stochastic assumptions like Brownian motion with drift or any other time series model. It's just each day there's a vector of returns for some underlying universe of n stocks, and he wants to maintain a weighted portfolio over those stocks and say something about it. And he actually says something stronger even than what I said about comparing favorably to the best single stock in hindsight. He compares his algorithm's return to the best constant rebalanced portfolio in hindsight. Okay, so what I mean by that, just so we're all on the same page, is that the sort of class that he wants to compare himself are all distributions over these n underlying instruments in which you do constant rebalancing. So you just have some fixed weighting, and then every day, some things make and some things lose money, and then you've made or lost money, but whatever money you have left, you're going to redistribute it according to this constant vector of weights. Okay, and as some of you might know, rebalancing is an extremely powerful thing. In particular, it's easy to kind of come up with very simple sequences of returns for even two stocks in which neither of the stocks is really doing anything at all. They're essentially flat. But because of the rebalancing, you're actually getting exponential growth in wealth. Okay? So Cover proposed a particular algorithm that doesn't look too dissimilar from the ones I described a few slides ago, and compares it to the best constant rebalanced portfolio after the stock outcome. So again, in hindsight for an arbitrary sequence of returns. But he compares to a stronger class of comparators, but he has a weaker criterion for what he means by regret. In particular, he looks at log wealth. So he wants the log of his cumulative wealth to compare favorably to the log of the cumulative wealth of the best constant rebalanced portfolio in hindsight. And this is all very, very sensible in the regime where you imagine that the best constant rebalanced portfolio is experiencing exponential growth, right? Because if you take the log and it's not exponential growth, this is not an interesting statement. Okay? Okay, and so he actually did some simulations. So here is a figure reproduced from Cover's paper in which there are two, n is 2 here. There are two underlying stocks. And here they are down at the bottom. And here he's showing the kind of cumulative return of those stocks and then the cumulative return of his so-called universal portfolio algorithm. And you can see this looks quite good. These stocks aren't doing much, and his is generally doing quite well. And not only does it have kind of no regrets to either of these stocks, it's doing much, much better. He doesn't, unfortunately, show what the best constant rebalanced portfolio would be, but there is a theoretical guarantee about that. And this is from a much later paper that proposed a similar algorithm for a similar setting, in which, again, they've taken some underlying universe, I think in this case of about 30 tickers, and they're not showing you the underlying tickers, but they are showing you the performance of their algorithm, which is here. This is the performance of the best constant rebalanced portfolio. So they're kind of comparing favorably to that. They're not doing as well, but they're doing almost as well. And this is the return of the best single stock in the underlying universe of 30. Okay? So this all looks well and good. And so maybe 10 years ago or so, when I started, or maybe more like 15 years ago or so, when I started thinking seriously about trading and finance, I was aware of this literature and I was aware of these papers, and I thought, well, this is an obvious thing to try. And I learned a lot in doing that, which is where we come to the asterisk on the title here. And so these are plots from some experiments I did. And in this particular case, I've taken a much, much larger universe than any of the previous papers considered. In particular, I took the S&P 500. Okay, so now instead of n being 2 or 30, n is 500. Okay, and what I'm showing you here is the S&P 500 between 2005 and 2011, which is a very interesting period for the S&P 500 because it includes the financial crisis and most of the recovery from the financial crisis, but to the extent that the index ends up in 2011 about where it started in 2005. So there's been sort of huge directional movement, but overall there's not been much change in the index from the start point to the end point. It's been a period of extremely high volatility. And so what I'm showing you on this left-hand plot is there's a blue curve for each of the underlying stocks in the S&P 500. This is each one of these blue lines is the cumulative return over that period for one of those 500 stocks. And these lines that are buried down here in the middle, again with a little red arrow, are the performance of the kind of multiplicative weights algorithm that I showed you before that has this no regret guarantee. And now it doesn't look so great. And there's many of these. I'll get to why there's many different colored lines here in a second. But you can see that, this does not look especially better than just trading the index itself, and it's not. Okay, you're not doing much better here with this particular algorithm than you would have done by just sort of equally weighting the 500 stocks at the beginning of 2005 and letting it sit, or rebalancing, for instance, over that time period. And what I've done over here on the right plot is taken away the other 500 curves here so we can just see the performance of the algorithm a little bit better. And the different curves here correspond to different values of the learning rate. So remember, I told you there's this one parameter of this method, which is how aggressively you make these updates. And if you set it to 0, then you're not doing any adaptation at all. You're simply parking your weights equally and leaving them. And if you crank it up really high, then you're making very, very dramatic changes in response to positive or negative returns. And so the green line here is where the learning rate is the highest, and the blue one is where it's the lowest. And you can see, like, to me, none of these look appealing, right? The blue one is kind of trading the index. The green one, looks a little bit better at the end, but then you had, of course, a much more significant drawdown during the sort of period of the financial crisis. And the real problem here isn't that the returns don't look great. That is a problem. The real problem is that the way you're not getting good return, which is with extremely concentrated portfolios. So in particular, if you crank the weight up to this particular green curve that I get here, this is what the underlying weights look like. So there are actually 500 curves in this plot here. You just can't see almost all of them because they're nailed down here at 0. And so you can see that all this green strategy is doing is wildly switching its capital and sort of chasing whichever thing is outperforming for a particular short time period. You can see that roughly when this particular stock takes off is when the algorithm sort of midway through the time period more or less puts almost all of its weight in that stock for the remainder of the period, right? And so even if you were sort of found these returns acceptable, from a quant perspective, you could never trade this, right? Like a quant hedge fund, Quantopian in particular, I believe, would never let you trade such a strategy because it's too concentrated, right? You're basically like doing stock picking. You're not actually doing something quantitative and with low concentration and high diversity. By the way, if you're interested in what this stock is, it is, of course, Apple. And so even though the algorithm is doing something sensible, and I would have been very happy for you to have told me in 2005 to put all of my wealth in Apple and just leave it there, still, from a quant perspective, this is not the sort of, kind of ex post behavior that you want to see, okay? And so this leads to the natural question of like, well, can we fix this? Can we adapt these algorithms and this framework, which I think is very appealing, where you're not making any stochastic assumptions and you're still getting these very strong ex post guarantees to an arbitrary sequence of data? Can we somehow preserve those properties but deal with the sort of additional constraints that come into a quant trading environment, which is you want things like a diversified portfolio and other forms, which is one form of risk management, right? Diversification, okay? And so, after doing these experiments, I spent, some time over the coming years writing a series of papers in which I tried to address these things. And let me tell you about some things that don't work. So one thing you could ask for is you could just say, like, well, look, of course, if your metric is to, let's say in a finance setting, to have the return of your algorithm compare favorably in hindsight to the return of the best individual stock or the return of the best constant rebalance portfolio, there's nothing in that statement that mentions anything about risk, okay, or concentration or Sharpe ratio or the like. And so one thing we could say is like, well, maybe we can just change the criterion and go back and kind of redo the math and work out an algorithm that will make a similar statement for the altered criterion. So let me be precise. Every individual stock not only has a cumulative return, it has a Sharpe ratio, right? We can look at the S&P 500, and after any time period, we could say, what is the Sharpe ratio of each one of these stocks over the time period in question? And I could therefore ask, can we design an algorithm that in hindsight has a Sharpe ratio which compares favorably, i.e. has low regret to the best individual stock's Sharpe ratio in hindsight? Perfectly reasonable question. Could also ask it about whatever your other favorite kind of risk versus reward trade-off is, like the mean variance optimization. I could sort of say like, well, I'm going to, for each stock, look at its return minus its standard deviation historically, and I want your algorithm to compare to whichever stock has the highest mean minus standard deviation. Okay, so this seemed like a good idea. And unfortunately, there are strong negative results on this. So not only could I not find an algorithm which gave me a mathematical statement like the one we saw at the beginning, but for, say, something like Sharpe ratio, even worse, we were able to prove an impossibility theorem. We were able to prove that you just cannot design an algorithm which will give you such a guarantee on an arbitrary sequence of returns. So no regret is provably impossible. In fact, not only can you prove that no regret is impossible, you can prove strong lower bounds on what's called the competitive ratio. So, instead of sort of getting optimal minus something, I could ask, well, maybe can I get half of optimal or 1/10 of optimal? So it's like some constant fraction of optimal. And you can even prove impossibility results for that. So there's somehow something about this framework which forbids you from changing to the types of criteria we might like to have in a finance setting and still kind of preserving the types of mathematical guarantees that we get. And intuitively, the reason for these impossibility results is that volatility introduces switching costs, right? So, I can be tracking a stock or putting all of my weight in one particular stock and enjoying the sequence of returns it gets, and maybe some other stock starts looking better, and so I want to switch to that other stock. Well, at the moment I switch to that other stock, I start enjoying whatever returns that stock is getting, but I don't enjoy the same historical volatility, right? So somehow standard deviation is somehow keeping track of some sort of state, and this state is causing problems for the no regret type of framework. Okay? So one thing that we had more success with, an alternative approach if you like, is to, instead of assuming that these black boxes or predictors are arbitrary, let's imagine that they have some risk consideration properties as well, okay? So in particular, let's internalize the risk within these strategies, and then if we have a collection of strategies that are doing some risk management internally, can we run an algorithm on top of those which has sort of favorable no regret style properties? And so let me just tell you a little bit about this in one slide. So this is what you might consider no regret learning under some sort of risk constraint, okay? And so as many of you know, like the Sharpe ratio is something you can always measure, but it's a very difficult criterion to actually manage to, right? The closest you can come to actually managing to the Sharpe ratio is to just impose risk limits, to control your risk somehow. And so in particular, one natural way of controlling risk is to restrict yourself to portfolios or strategies whose daily P&L has a standard deviation of at most a certain amount. So we're basically going to say, look, in a kind of hedge fund context, you might imagine saying, whatever the returns are, we want to restrict ourselves to strategies that on a typical day, won't have a standard deviation of, let's say, more than $10 million one way or the other. Okay, so we're going to basically, we have some underlying capital in a strategy. We can look historically at the P&L that's been generated on that capital and look at its distribution and say we just don't want anything whose standard deviation is more than a particular dollar amount. So if you do that, right, if for instance you go through the exercise of taking the historical returns of the S&P 500 and you estimate the covariance matrix between those 500 stocks, or you have some perhaps lower dimensional factor model for doing so, and you basically say, well, what are the portfolios over those stocks that have less than a certain dollar value of volatility historically, it's easy to work out the math that this is basically going to give you an elliptical constraint in portfolio space, and the eccentricity of that ellipse will depend on the strength of the correlation. So like if all of the stocks are independent, then this constraint on the standard deviation of your GMV is just a sphere in n dimensions. If some stocks are highly correlated, then you'll get sort of eccentricity in those particular dimensions, okay? Okay, so this is nice because it means that, if we sort of assume that the underlying strategies or portfolios that we're trying to track in a no regret setting are risk managed in the sense that they have some standard deviation limit on their, on their daily P&L, we end up with a convex, in particular an elliptical, but more generally a convex constraint on our portfolio space. Okay, and what I'm showing you in these kind of simulated plots are, just two strategies. One of which is essentially a momentum strategy. This is where there are two stocks. Okay, so there are two stocks here, and the X and Y values here are essentially indicating the position in that particular stock at different moments of time. And the color coding here you can ignore. It's just sort of, I think blue is sort of early in the data and red is later in the data. So I'm just trying to show you the movement over time. So in these simulated plots, all I'm showing you is one strategy that's essentially following a momentum rule and is therefore changing its portfolio over time. And another one is essentially a pairs trading strategy where there's it's basically offsetting long positions in one stock with short positions in the other stock. And the stocks are pretty correlated, which is why we have this highly elliptical shape here. So these are sort of two underlying strategies that we've imposed risk considerations on. So you can see that for either this momentum strategy or this kind of fully hedged pairs trading style strategy, they never leave this elliptical constraint, because if they hit up against the border, we just say, don't make that trade. Don't make any trade that would actually cause you to cross this risk constraint. And so now we've changed the game, right? Rather than considering arbitrary black boxes, we're considering arbitrary black boxes, but we don't let them go outside of this little playpen, right? Because we're enforcing a risk consideration on them. And now you can recover, the type of theorem I gave in an earlier slide. So now we're only going to compete with strategies that obey these risk limits, and we're also only going to look at strategies that make, as these strategies do, they only make local moves in portfolio space, and you can think of this as modeling, kind of limiting your market impact, okay? And to kind of cut to the chase, if you make the additional assumption that your underlying strategies are risk managed in this particular way, then you can give an algorithm that looks similar to, but is a little bit more complicated than the one I gave at the beginning, that will actually give you a no regret guarantee in the risk managed criterion, okay? Say like mean minus variance, okay? And the only thing you need to do is sort of kind of combine no regret learning with some tricks that are from an interesting literature called the pursuit evasion literature, which you can go look up, which has a long mathematical history, but it's basically about games in which one party is trying to chase another party, let's say in a convex region. And so you can recover theoretical guarantees, and you can get kind of nice experimental results as well. Let me just finish up here by talking about some variations and generalizations of this framework. So, one thing it would be nice is to maintain the original no regret guarantee I talked about, which is to have small regret to the best single predictor in hindsight, but also guarantee that you will never do much worse than some fixed index, okay? So for example, it would be great if I could say like, well, you'll get close to the returns of whatever the best stock is in the index, but you'll never do worse than the index itself, okay? Whereas the original statement allows you to do kind of cumulatively square root of t worse than the index, right? So if sort of everything's moving sideways and there's no winner taking off relative to the index, you might actually lose kind of square root of t regret to the index itself, which wouldn't be so great. So it turns out that you can make, again, slight modifications to the type of algorithm I gave you at the beginning of the talk and get this kind of guarantee as well. Sort of promise that you'll track the index, and if something in the index takes off, then your profit will track that as well. A very important generalization in many applications, but including in finance applications, is to go to what's called a bandit setting. So in the framework I've described to you so far, each day you're maintaining a weighting over these underlying predictors or stocks. But whatever weighting you're maintaining, even if you put all of your weight in a single stock, you're still finding out what the returns of all of the stocks are. Okay, and so that's fine if your underlying predictors are actually stocks. But in many settings, you might only get feedback on the thing that you chose to play, and this is what's called a multi-armed bandit problem for those of you that are familiar with that literature. So, for example, if instead of being n stocks, I have n strategies, and each of these strategies has internal state and makes trades each day. And I want to maintain kind of a weighting over these underlying strategies, to really find out what a strategy does on a given day, I really need to trade it, in particular because, I can backtest all of them, right, in parallel, but I can, to really find out what a strategy would have gotten today, I really need to trade it live in the market, among other reasons because of trading costs, right, because of market impact, because of the counterfactual that, if I make trades, that causes other traders and algorithms to change their behavior, and the only way of simulating that is by actually trading live in the market, okay? So in a setting like that, I can't just sort of maintain this conceptual weighting and every day find out what these strategies would have done. I really need to pick one or more of them and play it in the market to get the feedback, okay? And so this is called a bandit setting, where you only get the feedback or payoff of whatever choice you made that day. And basically, everything I've said in this talk also applies to the bandit setting. There are simple modifications of the algorithm I gave on the first slide, where you only get feedback from the thing that you chose, and you still get similar mathematical results with a worse regret bound. I think it goes, the dependence on the number of time steps goes from square root of t to t to the 2/3, something like that, okay? Let's see. The other thing that I think, tool that you should be aware of, and by the way, one of the reasons I wanted to give this talk is that these tools are simple enough but powerful enough that I think a lot of you could find applications for them in your own strategies. And so let me tell you about, kind of one of the biggest generalizations of this framework that's been known to date, which is sort of general online or sequential convex optimization. So now imagine your action space, instead of being picking between one of n discrete alternatives, which is really the same as maintaining a weighting over them. You can think of maintaining a weighting or distribution over them as a probabilistic strategy where I have a weighting and I'm going to pick randomly from that distribution and play the particular choice that I made, right? So mathematically it's exactly the same because it's just, either the inner product or it's an expectation, okay? So a very nice generalization of this is where our action space is continuous, right? So instead of there being n distinct choices, there's a continuous infinity of choices. But we need the shape of that continuous infinity to be nice, let's say, some convex and compact region. But if you want to think of a specific example, imagine that you have some parametric strategy class, okay? And that each point in this space is one setting of the parameters for your strategy. Okay, so a typical thing to do would be to get historical data and optimize the parameters of your strategy on the historical data and use that going forward. But then again, you're making the assumption that the future is going to look something like the past. So you can not do that and instead think in a no regret way and say there's this continuous infinity of settings of parameters for my strategy. I'd like to be able to promise that no matter what the data looks like, I will run a strategy whose performance in hindsight looks like the optimal setting of the parameters, after the data's come in, ex post, okay? And furthermore, let's imagine that the way the payoffs are determined each day is with some arbitrary convex function over your parameter space. So, the game is, if you like, is that everyday nature picks some arbitrary, potentially different convex function describing the payoffs over your parameter space, You don't know what that function is, but you pick one of the parameter points and you get the corresponding payoff that day. The next day, nature changes what that function looks like. You again pick a setting for your parameters. You can basically get the same kind of guarantee that I gave in the no regret setting, where you promise that no matter what the sequence of payoff functions chosen by nature is, the performance of your algorithm will compare favorably to the best setting of your parameters in hindsight. Okay, and this is sort of the most general formulation of the no regret setting. So just to conclude, no regret learning I think is something that I would encourage all of you to look at. It has very rich history, has very powerful theory that touches on many topics from finance to game theory and even sort of mathematical programming in the form of convex optimization, linear programming, and the like. On the other hand, deviations from the typical additive objective function like cumulative returns or cumulative payoffs kind of break the theory for the most part, which is not a great thing. But there are workarounds, right? So there's one workaround that I mentioned, and there are others. The one is to sort of endogenize risk levels within your strategies and then run such an algorithm on top of those risk managed strategies as well. And I've listed here at the end, the Quantopian team will make these slides available. I've just listed some references. I especially recommend the first two, which are very nice survey papers on the entire topic of no regret learning, and they're relatively recent as well. And I'm happy to take questions if there are any.
Okay, so first off, I'd rather stand. Okay, so first off, I just want to thank you for giving such an amazing talk.
Thank you.
I wish I had you as a professor when I was an undergrad, not too long ago. But what I want to ask about this is, I guess that when you have that the payoff of the algorithm, the performance of the algorithm, I guess it depends on how you would define, the payoff that you're aiming at. Like, if you have a collection of n strategies, then I guess it just become more concentrated if you're saying that what you're aiming at is total cumulative return over the entire backtest, as compared to, say, the total cumulative return over the past 3 months, 6 months.
I see. So you want to have kind of a sliding guarantee. So this guarantee, there are variants that give you this as well, right? So rather than sort of saying like, well, t just keeps ticking up, and I always will promise that I'm like square root of t behind at worst the best thing on the entire history so far. I might want a moving guarantee, right? That basically says in any window of length, let's give it a different name, of any window of length t prime, I will compare favorably to the best thing on that window. You can get such a guarantee as well.
Okay.
But in general, like that fixed window t prime won't be going to infinity, right? Because it's a fixed window. So if I want to, you should think of it as like it is a learning algorithm, right? It's sort of getting better in the sense that the guarantee that you're giving is getting stronger the longer time goes on.
Right.
But if you choose to compare yourself to a fixed moving window of like 250 trading days, right, the last calendar year, then that value will be fixed, and you'll track to that extent, but you won't have as strong a guarantee as you would if you let kind of t go asymptotically to infinity.
Okay. It just seems like that the classic momentum strategies, like they seem to sort of mesh pretty well with this no regret.
So that's a good point. This is a momentum strategy. Cover's thing is a little bit different, right? Because you're running it on top of constant rebalance portfolios. So there's both momentum and reversion going on, because the meta algorithm that's reweighting underlying portfolios, that's momentum. But the constant rebalancing is a reversion process, right? When you rebalance, you take money away from things that did well today and you give it to things that didn't do well today.
Right.
So in the universal portfolio case, there's both a momentum and a reversion aspect.
Right.
But in the straight versions where you're just comparing to the underlying N stocks, for instance, it is a pure momentum strategy. You're right.
All right. Oh, that's pretty cool. Okay. Thank you.
Yeah, actually, I have two questions about this. The first one is that I'm a little bit confused about why risk sort of derail the algorithm. I would have thought that the theoretical proof has already incorporated all possible random deviation, from the mean, so that despite the presence of risk, it still satisfies that convergence.
Yeah. So. Let me try to answer that question even more generally than these methods, in which may be a more or less satisfying way of answering. In general, one of the dark secrets of all of modern machine learning is its reliance on additive objective functions. So what I mean by that is you have an objective function that you're optimizing that can be decomposed as a sum of the objective functions on the individual data points. Okay? So for example, least squares regression, right? I can write down the objective function as a sum over each data point of my squared error on that data point, okay? And basically everything you know from modern machine learning, almost everything, relies very heavily on that additivity, both the theory and the practice, okay? And anytime you have an objective function which breaks that, various chaos ensues. And the simple thing that happens here is that square root does not have that property, right? If I look at like the variance of a random variable or like the performance of a model over time, it's a square root of a sum, okay? And you can't rewrite a square root of a sum as a sum of square roots, okay? And this is what so that's sort of a math answer. The intuitive answer is that things like variance and standard deviation and other common risk metrics, they actually have state, right? Another way of saying less mathematically what I just said is that if you give me a list of, if there's a list of numbers and you tell me that there's n numbers in the sequence and I want to know what the contribution of this number is to the average, I know exactly what it is. It's that number divided by n. If you ask me what the contribution of this number is to the variance of that sequence, I can't answer you. I need to see the rest of the numbers. And so things like standard deviation and variance, you can think of them as having state, right? You're actually keeping, there's something about there's global information about the sequence in that number in a way that's not present in things like just the straight mean or any other additive loss function.
Okay, thank you. So the second part of my question is the slow conversions. I understand that you have a sublinear convergence to the best algorithm. So the question is this too slow for a practical, trader?
I guess my answer to that would be if it depends on depends on how much data you have and many other things. But my general answer would be if sort of 1 over square root of t convergence to optimality is too slow for you, then so will all of machine learning, right? Because basically sort of power law convergence is the rule in machine learning, both theoretically and largely empirically as well. So, I definitely agree there are data sets for which the T we have is just, not big enough for these things to make interesting statements. But in general, that's a sign that you just don't have enough data to apply very, very simple learning methods, even like linear regression, for example.
Thanks for a great talk, very thought-provoking. So my question is in regards to the multi-armed bandit.
Yeah.
Can you talk a little bit about the exploitation-exploration trade-off and how you sort of handle that?
Yeah, it's a good question. So sort of no-regret algorithms in the bandit setting essentially work on the principle, they handle exploration, exploitation with sort of an optimism under uncertainty principle. And what I mean by that is like a classical bandit algorithm that did very explicit exploration exploitation would be something like, look, at each round, with high probability, choose the thing that's done the best so far, and with the remaining probability, pick something at random, and then sort of gradually schedule that exploration probability to go to 0. In sort of the no regret framework, you instead have implicit exploration. What you basically do is you say things that I've tried a lot, like it's going to sound like I'm making probabilistic assumptions, but I'm not. But the intuition in a probabilistic setting would be things that you've tried a lot, you have very tight error bars on what their real underlying value is. And things that you haven't tried that much have very wide error bars. So instead of using like the empirical mean of each one of the actions so far, use an upper confidence bound, okay? And so things that you haven't tried much kind of get this automatic promotion, and then you try them more, and then you find out whether they're really good or not. And this is basically how all these algorithms look.
Awesome. Thanks so much.
Hello. So you showed that once you manage the risk of your strategies, you could get good regret guarantees. Now, what is the intuitive reason that you didn't get it when you didn't manage the risk?
What's the intuitive reason why what?
Like, theoretically, you should have gotten it without managing the risk, as your theory showed initially. So what is the intuitive reason when you manage the risk you could get
So no, what I'm saying is the original theory all breaks if you don't kind of have each one of the constituent strategies managing its own risk in some sense.
But only in the experiments, right?
No, even in theory,
Okay.
right? In theory, I can just sort of give you bad sequences in which the underlying constituent strategies are not risk managed, and not only will the particular algorithm I showed do poorly, you can actually prove outright that there doesn't exist an algorithm which will kind of recover the theoretical guarantees I gave on the early slide. Okay, last question.
Thank you, Dr. Kearns. I have a question about updating the weights to optimize the Sharpe ratio. Can we consider using some like momentum gradient descent method that we can update the, instead of doing like stochastically, we can add the everyday's information with respect to the gradient of the Sharpe ratio, so that we can use some momentum method that match the idea that you use here to like
I'm afraid
updating the weights.
My answer is going to be the unsatisfying one, which is, nice idea, it just turns out that doesn't work. Okay, so like as per these impossibility theorems that I mentioned. So by the way, you can interpret these algorithms as momentum algorithms engaging in gradient descent. So in particular, this last generalization I mentioned, where you have like a convex parameter space, and each day nature's picking some payoff function over that parameter space, and you're sort of trying to track the best setting of your parameters. If you go look at the actual algorithm that does that, it's essentially, even though there's no gradient to speak of, because every day the objective function is changing according to nature's choice, it's essentially trying to compute some sort of aggregate gradient of the functions chosen, the average of the functions chosen by nature so far. So these algorithms, in general, they are momentum algorithms, and they are following a gradient, but sort of trying to do it with Sharpe ratio as the objective just kind of breaks all of the theory, and it's because of this sort of non-additivity that I mentioned before.
Okay, thank you.
Okay, thanks everyone.